There you go. It's
Okay.
working.
Oh, perfect. So can you send that to me a little bit later?
Yeah.
Okay, perfect. I can put another file in. That's great. Then everybody can have the whole review, and I don't have to re-record anything later. So I got most of it on here, but we'll get a little more on there.
Yeah.
Great.
Yes.
Hi, everybody. We're back. Okay, so yeah, the idea is now, after the end not term, all of these remaining terms are over here in this neighborhood, which is disjoint from this neighborhood, right? So in other words, what we actually could say is that, like if we measured the distance from xn to y, let's see if we can do that, for all of these ends, right? So what we could do is we could go ahead, I'm just kind of winging this right now, just so you know. We could just add and subtract x, and then we could use actually what I really wanted to do though, hold on, I actually want to go, I want that to be greater than, epsilon over 2, don't I? So, I mean, it's kind of, okay, back up a second. So, if n is greater than or equal to n naught, then the distance from xn to x, this distance is less than half of the distance all the way between these two, right? So, and that whole distance is y minus x, so we're dividing that by 2. So all I'm trying to say is that if xn is less than epsilon from, maybe it would help to just also think of this, this is y minus x is equal to 2 epsilon. So this distance is less than epsilon, so then this distance has to be more than epsilon. That's really all that I'm saying. Right, that's all that I'm saying. So the distance from y to x is just less than or equal to the distance from y to xn plus the distance from xn to x, right? Just the triangle inequality. And this one is 2 epsilon, right? And this one is less than epsilon right here. So this would be less than y minus xn plus epsilon. So, solving that now, the distance from y to xn is greater than epsilon. Okay, this is the calculation that I was looking for. That's what I was looking for. So, is everybody following that? Basically, this is the key argument here. And this implies that the distance from y to xn is greater than epsilon. Which just means that, xn is not in the neighborhood y minus epsilon to y plus epsilon. It's not that close. Right? So that's how we put that together. Now, the problem is that before we get to the n naught term, x1, x2, and x3, those first few terms could be anywhere, right? They could be absolutely anywhere in here. So, you know, x1 could actually be here, x2 could actually be here. So now's where we can do the minimum thing. We can take the minimum of the remaining points. Okay, so what we really would want to do then is kind of have to start over with the proof, don't we? What I'm going to say is choose epsilon equal to the min of absolute y minus x over 2, and then absolute of y minus x1, y minus x2, etc. Okay? Like that. Gosh, there's another technicality I've just realized though. What if y was equal to x1? Right? Even so, it could be that y is equal to x1, and then, right? Then later on, the terms start moving away from y and get closer to x. So this is going to be greater than 0, and for that, I'm assuming assuming that y does not equal x1, x2, and so on. And this goes, sorry, I said dot, dot, dot here. Let me be more careful. This is going all the way up to y minus x n naught minus 1. Okay. That will be greater than 0, provided y does not equal x1, x2, all the way up to x n naught minus 1. So all of these have to be positive values. Okay? They all have to be positive values. Guys, this part over here, you can just assume that. Okay. Because if your sequence is converging to x and the first couple of terms happen to hit y, you can just throw those terms away from your sequence and just start your sequence after you get to the later terms. So just go ahead, you can assume that y does not equal any of these terms. Okay, maybe that would have been, it would have been an easier question if I just said, prove that if y does not equal x and does not equal any of the terms of the sequence, then this is true. And I'm okay with that as an assumption. Okay, so if we choose that, then I claim that this problem is going to work then. So so then there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, the absolute value of xn minus x is less than epsilon. Thus thus x does not equal y, basically. Okay, so y does not, well actually what we're trying to say, sorry, hold on. The neighborhood y minus epsilon to y plus epsilon, okay, minus y, let's take out y from that neighborhood. That neighborhood, that's a very small neighborhood, right? This neighborhood is small enough that x1 is not in it, x2 is not in it, x3 is not in it. None of those are in it because those are all still too close to these distances are all at least epsilon, maybe more. They're too far, right? None of those terms are in there, and neither is x because of this assumption. So this intersected with the sequence xn, where n is a natural number, is empty. So there's no terms of the sequence in there, and so thus y is not an accumulation point of the sequence. Okay, that took a little bit of work. Probably this is a little too hard for what I would ask, but if I made some assumptions to make it easier, then it would be fine, such as assuming that y does not equal any terms of the sequence. You guys following it? I actually think the easiest thing is to help you is the picture, right? So you have x here and you have the sequence here converging to x, and then y is over here somewhere. So after a certain point, all the terms are within this neighborhood, and the first few terms, right, they are a distance away from y that we're going to exclude by taking the minimum of each of these individual distances. So your epsilon is quite small here. The epsilon is quite small. Everybody good with that? Make sense?
So can you do the line after that with that one?
This one? Oh, I'm just using the definition of that. So given an epsilon, here it is, there has to exist an n naught such that this is true for all n greater than or equal to n naught. Exactly. Okay. And so then I use that to then wait a minute. This still doesn't work. this still doesn't work. I just figured out that it still doesn't work. So in my solution, I realized what I did. In my solution, I just assumed that the y was not equal to any of these terms here, so I didn't really have to worry about it. My problem right here with this proof is that I say here that there exists an n naught, and that n naught is based around an epsilon, but the problem is that this epsilon was already defined in terms of an n naught that we had already found over there. So what I think I need to do to fix this is to just change this to a different n. Let me call this n1 in the natural numbers, such that as long as n is greater than or equal to n1. I don't want people to think that this n1 is the same as the n naught. Okay, then we're okay. It's a little tricky. I had to get this n naught first, right? Such that the sequence is within epsilon of x. And then I have all of these first few terms. I take the minimum of those, and then I go back and I re-figure out my new n naught, but I'm going to call it n1. This n1 will, if anything, be bigger than n naught. Okay, because your epsilon, like, look at the epsilon you found here. This epsilon gave you this n naught. Well, if you look at this epsilon, it's smaller, because you have the same y minus x over 2 plus some more stuff. So this is an even smaller epsilon, so I would expect an even bigger n1. Okay. It's a little technical. I think it would be better as a question if I had phrased it as assume that y does not equal any of the terms of the sequence, and then I think it would be a little bit cleaner to write up. My solution is definitely too simplistic here. So, okay. I did that one. Okay, let's see. Which other ones I want to do here. Okay, let's do this one next, okay? We'll do number 7. So this is hopefully helping you remember, sort of think about what things you need to review. Okay. Let's do this one. This one will be a little bit easier. So number 7. Does this converge or diverge? And of course I want to prove. So the first, it's a sequence. The first term is just 2. And then the n plus 1 term is just the square root of 2xn plus 8. This would be for n greater than or equal to 1. So we have that sequence. So we make a sequence out of that. Any thoughts what we should do here? Plot some points. I like plotting some terms. Good. So x1 is 2. What would x2 be equal to? Is this directly? This is not for homework, is it?
Reviews. The practice problem?
Oh, is it? It is right off the homework?
No. Like
It's
the
similar
exact
to it.
similar to.
Okay, it's similar. I don't mind doing it. Okay. Okay. So x2 would be what? Square root of, yeah, so 2 times 2 plus 8 would be the square root of 12, right? Which is actually 2 radical 3. Okay. All right, good. And x3,
Yeah.
the square root of, what is that? 2 times the square root of 12 plus 8, right? Actually, you could simplify that also, but, okay.
We can just change the substitute with it instead of the radical 12, we'll do the 2 radical.
Oh, okay, so then that would be the square root of 4 radical 3 plus 8. And then if I wanted, I could pull out a 4, which would give me a 2 here, and this would be the square root of the square root of 3 plus 2? Or something like that? Yeah. It's getting pretty ugly, isn't it? All right, well, so much for that idea. At this point we say, this is too much, I don't want to do this one. No, so what's going on here? Are the terms doing anything in particular that you can tell just from what we have?
They're increasing.
They're increasing, aren't they? Each radical is bigger than the one before it, right? So it might be true that it's increasing, okay? So what does that make you think of?
If we can show it's monotone, increasing, and then it converge.
If xn is monotone, and what's the other part?
Monotone increasing and it's bounded.
And bounded, right, okay. Monotone and bounded, then xn converges. Exactly. Then xn will converge if that's true. Make sense? Okay, so let's see if we can prove these things. I like to prove the monotone part first because if I can prove that, then the half of the bounded becomes just the first term is the bound, right? So let's try and prove monotone increasing and just see, even though we didn't get a very good look at what these terms look like, maybe we can prove monotone increasing without too much trouble. In other words, we're going to claim that xk is less than or equal to xk plus 1 for all natural numbers k. Try and prove that for every natural number k. So x1, so we also have to do a base case. Make sure you choose the right base case. It should be the smallest value of the subscript that makes sense. So k equals 1 is the first one. So x1 less than or equal to x2 is what we are testing. Well, we've already got x1, it was 2, and x2 was 2 radical 3, so sure enough, that's true. It's easy. Okay, and now we want to show that x sub k, so let's assume by induction that x sub k minus 1 is less than or equal to xk, right? And now I'm going to try and show that xk is less than or equal to xk plus 1. Just hopefully by induction. So xk, what could I do with xk then if I want to? So we need to show xk less than or equal to xk plus 1. This is what we're trying to do. Replace this one with the formula, right? So this would just be the square root of 2 xk minus 1 plus 8, right? Okay, now what?
So now we can change the xk minus 1.
Change it to something else?
Yeah, by doing it.
So you already used this. We're done with this. We plugged that in already. What else do we have?
Now we have to use the xk back.
Yeah.
No, we're trying to get to xk plus 1.
So
Xk minus 1 is less than xk, right?
Mm-hmm.
So I can plug that in right now, right? Just change the xk minus 1 to xk. Like that. That look okay? Oh, well then that's it, because this is equal to xk plus 1. You know, if you get stuck, you could always work backwards. Say you get stuck in the middle, you can come down here, write out what this equals, and then compare with where you are, and then maybe it'll be more obvious what's going on. So we're using the assumption right there in that step. Okay, so it is monotone increasing. Agreed? Are you happy with that? Okay. So then we have to show that it's bounded. Okay. What can you tell me about the bounded part? What would we already know? Okay, good. It's bounded below by x1 equals 2. Okay, so all of the terms are going to be at least 2. So far, so good? What is it going to be bounded above by? I mean, you could say, oh, it's going to be bounded above by 1,000,000, and you're probably right, but you're going to have a hard time proving that if that's not the sort of the tight bound. that you want to have. You don't want to just pick some number in outer space that's like huge and just say, oh, that'll be my upper bound. I mean, because you'd have to prove it. So how would we find out what we think would be the good number to use? We had those messy expressions earlier that weren't really telling us what we wanted.
So we're gonna have x equals square root of 2x plus 8.
Yeah, let's take a gamble and assume that this is going to work and it is going to converge and say, you know what, I don't know what it's going to converge to yet, but let's say it converges to x, right? Then this x would have to be the same as the square root of 2x plus 8, right? It would converge like that. Now you can try and solve this by squaring both sides, right? X squared equal 2x plus 8. All right, so x squared minus 2x minus 8 would be 0. So x minus 4 times x plus 2 equals 0. So we get x equals 4 or x equals negative 2. So you could do all of that calculation, right? Make sense? Okay, good. So we have a monotone increasing sequence. It's bounded below. And now, what do we think it's going to be bounded above by?
By 4.
Aha, this one, right? That would be a good guess, okay? So let's claim that xn is less than or equal to 4 for all n. That would be my guess. That would be my guess. Okay. So, how do we prove this claim? By the way, you throw away the negative 2, of course, because you know that's not in the right realm. Okay, that can't be right. So let's try to show that xn is less than or equal to 4. And I'm going to do that how? Anytime you're proving for all natural numbers, induction is the best way to go, right? So let's check it out. x1, this is the base. x1, well, x1 was equal to 2. That's definitely less than or equal to 4. Check. Okay, so that looks pretty good. And then we have to do the step. All right, well, let's assume that xn is less than or equal to 4, and then we need to show xn plus 1 is less than or equal to 4. This would be the next part. Okay. Make sense to everybody? Okay, so let's try and tackle this. xn plus 1. We want it to be less than or equal to 4. What can we do? Okay, we have the formula. Let's just write it into the formula here. It's going to be the square root of 2xn plus 8.
Are we just going to solve for xn?
Well, we just want to get this to be less than or equal to 4. So I don't know what xn is, but this is what I have right now, and I have the induction step is what I'm working on.
Oh, assume that
So,
xn is equal to 4.
This one, right? You got to use this is the assumption, right?
Yeah.
Okay. So let's just plug that in, right? Replace this with 2 times 4 plus 8. Just, in other words, just put in xn less than or equal to 4. Well, that is the square root of 16, which is 4. There you go. Looks great. Easy, right? It's actually pretty easy. These are usually pretty easy. This one is a little tougher than some of them in the sense that you actually have a hard time if you write out the first 2 or 3 terms. You can't really see what's happening. So you need to take this gamble right here. This was the key thing, was suppose it does converge, right? This equation that allows you to solve for the x that you're expecting to see there. Okay, did that, I did that. Oh, here's one we haven't done that maybe I should do. Okay, at least a couple more. What is it? 4:30. I have at least a couple. This might actually end up taking until about 5 anyway. Okay, it's 4:35 right now. I've got a couple more problems. Okay, and I'm just kind of doing one example of a lot of different things. There's obviously more things to practice too, but. So let's try this one, number 8, I think. Determine the limit. Okay, so I'm going to give it to you right here. The limit as x approaches 0 of, and this is just a big fraction, the square root of 1 plus 2x minus the square root of 1 plus 3x, all divided by x plus 2x squared. There we go. So, of course, you put in 0, you get, undefined, right? That'd be too easy, right? It'd be too simple. So, it doesn't tell you how to do it. It doesn't say you have to go to the definition or anything like that. So you have some choices what you can do.
Can we use manipulate the function by algebra like multiply by the conjugate?
Okay, excellent. You guys all got that, right? Multiply this by the conjugate on the top and the bottom. So let's do exactly that. This would be the limit as x approaches 0. So on the top, I have the square root of 1 plus 2x minus the square root of 1 plus 3x. I'm going to conjugate that by the square root of 1 plus 2x plus the square root of 1 plus 3x. And I'm going to do that on the top and on the bottom. So x plus 2x squared times the square root is a lot of writing. Okay, all of that, yeah. A lot of writing on that. Okay, so what can I do next after I've conjugated it? Should simplify, shouldn't it? On top, we'll have radical 1 plus 2x times itself. Well, that's just 1 plus 2x. And then the outer and inner terms of this FOIL will cancel. And then I'll have a minus on radical 1 plus 3x times itself. So we have 1 plus 2x minus 1 plus 3x. And then on the bottom, x plus 2x squared. And then radical 1 plus 2x plus radical 1 plus 3x, like that. Okay, great. And actually, when we simplify the numerator, let me just do it right here to save some time. We're just going to get negative x, right? Okay, so what can I do from there?
Factor in x on the bottom.
Okay, if I factor in x on the bottom, then what can I do?
And then use cancel the top.
Cancel it with the x on the top. Why can I do that? Why can I cancel the x from the top and the bottom?
Because everything is multiplication, but we just
So you can factor out an x, can't you?
Yeah, that's what we're going to do. We're going to factor out an x and then cancel it with this. But why can you cancel, though, is the question. So, if I have the limit as x approaches 0 of x over x, right, why can I cancel that and say that it equals 1?
The limit.
By the limit theorems.
So, the limit theorems, no, because the limit theorems would say this is the limit of x divided by the limit of x, and that would be 0 over 0 again. So that's that. You can only use the limit theorems if the limit of the denominator is not 0. Well, here the limit of the denominator is 0. So I can't use the limit theorems on that, but there's a reason why I can just get away with canceling these x's right here. Is x equal to 0?
No, it's approaching 0.
It's only approaching 0. The x's that you see in the definition of this limit will not be 0. They will be within delta of 0, but not equal to 0. So you're canceling non-zero numbers from the top and the bottom. That's the reason. It's really the definition. Yeah. Okay, so we can cancel. I just wanted to make sure we all had that reason down. So I have negative 1 over, and then on the bottom I'm going to have 1 plus 2x times the square root of 1 plus 2x plus the square root of 1 plus 3x. Okay, got it. And now, what can you do?
now you can use the limit. Well, now you can start using the limit.
You can now start using the limit theorems, exactly. So the top is negative 1, right? On the bottom, when I put in 0 here, I just get 1. And over here, when I put in 0, I get the square root of 1 plus the square root of 1. Okay. Now, one little question about that. That's actually not, when I'm plugging in 0 for x into this radical, that's not actually the limit theorem. Remember, the limit theorems don't have radicals in them. That's using the fact, why can I just put this and replace it with that? It's because we showed in, I think it was in a group work, that the square root function is continuous. So the limit of the square root of function as x approaches a point is just that point plugged in to it. So this is since radical x is continuous. It's really continuous at every single point of its domain. I will also say at 0. It is continuous at 0 as well. Okay, so then my final, and then everything else is limit theorems. The top, the bottom, splitting things up. So that all becomes negative 1/2. That would be the answer. Negative 1/2. Does that make sense? Negative 1/2 is the answer. You'd never guess that from the start. It turns out that is the right answer. Good enough? Okay. Any questions here? Might be good after the review. Go home and I will type all these questions up. Make sure you can do all these problems again. Practice them again. No such thing as too much. All right, I'm going to give you one more. And then I'm going to see how you're doing. I might call it a day at that point. Get off my feet a little bit. I've done just about everything that I have here. So do one more. This is number 9. To prove the limit as x approaches 2 of the square root of x plus 2 equals 2. Suppose you're proving that. This is true. This is true. Suppose you're proving this. Then suppose you are given epsilon equal to 0.1. Now, I'm actually going to give you an epsilon value. I don't think I've ever done this before. A specific numerical value for epsilon. Okay, and here's the question. What possible delta values can you apply in the definition? Okay, so what deltas would be acceptable to solve this problem? What deltas could we use here? That's the question. So maybe we should write down the definition one more time. So the limit of f of x as x approaches c equals L. That just means for all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than absolute x minus c is less than delta, then absolute f of x minus L is less than epsilon. Okay? So we have an epsilon given to us. Does anybody have a suggestion how we would find a delta now for this problem?
So maybe we're gonna work with that and
It's like doing the scratch work, right? Except this time I have a specific number for us to work with, right? So if I come over here and I think about scratch, right? So let's do that. Let's use the absolute value. The f of x is, of course, square root of x plus 2. The L is just 2 less than epsilon. This is kind of where we're starting from. Okay. So we have that. And by the way, the C is equal to 2, right? C is equal to 2. Got that one?
We want to make that one look like x minus 2. Absolutely.
Yeah, we need like an absolute value of x minus 2 into this thing somehow. Okay. Very good. So do we see how?
But are we gonna blend it with epsilon?
Yeah, this is point 1. This is point 1, so we can certainly put that in there. Okay. So in other words, the distance between this and 2 is at most point 1. Does that tell us anything about, let's try and do a double arrow here. Does that tell us anything about the value of this square root of x plus 2?
It's less than 2.1.
Yeah, it's less than 2.1. It can't be any more than that, and it's greater than.
Negative 2.1.
Hmm?
Negative.
It's greater than 0 for sure, but we can do better than that.
1.9.
Yeah, 1.9, right? See, you actually don't even need. See, as soon as you write this down, you don't even need these absolute value bars because this is definitely. Well, I'm sorry, you do need the absolute value bars, but the point is that this difference will be between negative 0.1 and positive 0.1. So this number is at most 2.1, but it's at least 1.9. Okay.
And now we can just square it.
You want to square everything?
Yeah.
Okay, exactly. So we're not really doing algebra so much. We're actually literally trying to solve this for x. So if I square both sides, 1.9 squared, I believe, is 3.61. And 2.1 squared is 4.41. My 7th grade math teacher made me learn all the perfect squares of every number up through 50 squared. And she would give us these tests and we'd have like 5 seconds to write down the answer, then she'd make us put our pencils down immediately. It was like she totally thought we should like memorize it. So I know 19 squared and 21 squared. These are like numbers I had to know like really fast. That's the only reason I know them. Okay, so we got that. So then, okay, so that tells us then that x is between 1.61 and 2.41. Okay. So let me just draw a number line here. Here is 2, right? X is approaching 2. 1.61 is like right there. This distance here, and then 2.41 is like right there, and there's another interval like that.
You take this lowest distance, right? So we subtract 2.
Right, this is 0.39, this one is 0.41, right? So we want to make sure that, so for all of the x's in this window, our scratch work will work, right? So we want to make sure that we choose a delta. Remember, you're choosing a delta around 2, right? So I could choose delta to be like that, or like that, or like that, as long as it's centered on 2, and it's not big that it excludes, that's beyond this interval. So what's the biggest that the delta could be? Obviously it's greater than 0. What's the absolute largest that it could be?
2 minus 1.61.
Which is?
0.39.
0.39. Yeah, that's it. Okay, and it actually could equal 0.39 because eventually x minus c has to be less than delta. So these would be the deltas. It says what possible delta values can you use in the definition. As long as it's less than or equal to 0.39, it's going to be okay. It's going to be okay. If it's bigger than 0.39, then you're going to be getting some x's over here that you have to consider, and for those x's, this isn't true anymore. Okay, so that's how you would do one of these problems where you actually have a specific delta to find based on the epsilon. Okay, so that is an example of actually applying the definition. You might want to go back. I don't think I'm going to do one right now because I'm going to give myself a break. But you might want to go back and just think about some of those examples where you had like quadratic functions and you had to actually do it from the definition. Remember where you have to do? We didn't really do a great example of that today, where you have to like choose a preliminary delta, shrink the interval that you're looking at down, and then solve for another delta in terms of epsilon, and then take a min of those things. So there's some examples of that from the lecture, also from the homework. Might be worth looking at those again, but done pretty well. It's just almost 5 o'clock. I think I've covered Actually, to tell you the truth, there's not a massive amount of stuff here. There's limits, continuity, monotone convergence, monotone subsequence. Using sequences to disprove limits or continuity, you want to be able to do that. Cauchy sequences, and some limits at infinity as well. Those are going to be the main things. Be able to state, obviously, the Bolzano-Weierstrass theorem, the definitions of Cauchy sequences, continuity, all of that kind of stuff. You'll see it on the sample test. You'll see where I'm asking you to just make some definitions. So you'll get a lot of free points if you know all those theorems and definitions, but you have to know them really well. They have to be stated precisely. Too many people did not get enough points on that on the first test, even though they had the idea. It was too vague, right? On some of these harder conceptual problems, I'm a little more forgiving if everything's not exactly perfect, but the idea is there. But on the definitions and the theorems, it's got to be exactly right. Not even one word out of place. I mean, I'll accept a word out of place if it doesn't change the meaning. But if there's even one word that changes the meaning, I'm going to really hurt you bad on those points on that. So make sure that what you say means what the definition is supposed to mean. Okay? Great. Thank you for helping me with that. You can shut that off anytime, and I'd love it if you'd send it to me. I'll be posting all these up so that people can watch them.